Anyone from the audience? Pravarshi, Arpita, Namala, Anant, Mustafa, Sandeep, Ayush, Rizwan, Shakti, Rupak, Shirish, Skandan, Maninder. If anyone has any query, you can just bring it up right now. Ganesh, Juan, Gautam, Manoj, Kranti. So Rupak has a query for bigger circuit, any use of ML to dig out partition?
Yes. Rupak, yes, actually we have a couple of machine learning techniques that we use for large IPs. IPs like PLL, SERDES, or IOs and IO bricks. So that is used to find out some of the analog parts that there is no algorithm currently to identify. And it's just done with the machine learning pattern matching algorithm where it can find and detect that this is the current mirror or this is your um, other pieces of a PLL, and it does the partitioning only for the active portions of the design, and that's how it achieves the speed up. So yes, the answer is yes.
And Anand has a query, which one is preferred over CCS or ECSM models?
I'm not an expert, but what I've seen in my limited experience, CCS is default. Now, some of the customers, even at 14 nanometer, at 10 nanometer, they will ask for ECSM, and the reason is that Cadence tools they would support CCS, but they claim that their accuracy is better with ECSM format. So Cadence continues to force ECSM format generation. Typically, most customers have both flows, but the dominant flow wins. So both are still going on hand in hand. But TSMC by default gives, actually TSMC also gives you both. Yeah. So from the customer data, I don't have a clear winner. But from the format point of view, a Mentor, for example, does not support ECSM in all their softwares.
Anand, does it answer your query? So Anand has another query. So I think he uses always CCS in many bike. So Anand, I didn't get the query. Can you just say it for everyone? Yeah, Anand. Okay. So Anand mentions that we use always CCS in many by customers / EDA. So,
Okay, it's just a comment.
It's just a comment. Yeah. All right.
Yeah, it's taking longer than I thought.
So why don't we move with a couple of concepts and then we'll come back to this one?
Right. Yeah. So that's a good idea. Let's do that. So receiver model. So we're going to cover this. Okay. Other constraints. So there are other constraints also that GUNA supports, and most of the popular ones are setup, hold, recovery, removal, and minimum pulse width. And all of them are supported by GUNA. And then there are some complex ones like half arcs and combinational rise and combinational falls, and some of the clock gating kind of constraints. All of that are supported by GUNA, and so some of those are peculiar. Most of them are identified by GUNA just by looking at the circuit, and it can do the right thing. But if it doesn't, then you always have an option of modifying the CDF and let it do the work. For constraints, actually, there are a lot of options for constraint, and for each one of the characterization, you have the option to turn on and turn off right in your lib.cfg file. So these are some of the options, config options that GUNA gives you. And this is an application. Okay, it's still running. Okay, so this is the application of your CCS delay calculation. How CCS delay calculation takes these models and gives you cell delay and wire delay. I kind of worked on static timing analysis about 10 years ago, and 2007 CCS was kind of hot at the time. 40 nanometer was new and everybody wanted to get their hands on CCS, and um, I was the first one to design even before prime time, when I was working for a smaller company doing the STA delay calculation. And the way that the larger algorithm works is essentially you create your timing graph, you load your SPEF parasitics, and then you compute your SDM. SDM is a simplified driver model. And the way you do that is first you do library lookup. And you already know slope because graph gives you slope by propagation. And you guess a C effective. So the C effective guess is essentially you can start with the summation of a pi load, and then you can come up with the IET looking at the CCS model. So given the slope and load, you get the current waveform. With that current waveform, you go and find the voltage across C effective. And once you have that voltage, you find out if the C effective. You go and find out the voltage across original interconnect. You replace your pi model with the large model, and then you compute moments using AWE or Prima or RISE or whatever algorithm you're using. It gives you moment, and then you use the moments to compute the slope at those receivers, and see if it matches with your receiver. So if the C effective, if the voltages don't match, then you compute and take a new guess on C effective, and that could be a binary search or a linear search, depends on your algorithm. And then this goes in the loop until it terminates, and you return the time and voltage at that point. So that's the effective algorithm. The most complexity comes in where you want to compute the waveform of net RC network, yeah. So for that, we ended up using another paper from Vivek Raghavan. That was part of SPICE at the time. SPICE also uses AWE in their modified nodal analysis. So it's the same algorithm that's used inside delay calculation of static timing analysis. So this is how CCS models are used to increase your accuracy in static timing analysis. All right, that's finished. So let's see. So we were hoping to see the synchronous and asynchronous arcs. Let's see. D has nothing. We did not characterize our setup and hold. RN. Okay. So it has ECSM capacitance and receiver capacitance. And same thing here. SI. Same thing. So these are input pins. We will see the arcs in output pin now. Okay, we have output pin here. So pin Q. Okay, let's see. So this is the synchronous CK-to-Q. So this is related pin CK, and this we are inside the pin Q. So this is CK-to-Q arc that we are looking at here, and this is non-unate, but it is rising edge, so this is sequential. These two things, timing sense and timing type, they tell you it's sequential or combinational. Timing sense could be not non-unate for a combinational, for example XOR, but then there won't be any timing type for XOR. So timing type makes it sequential, and rising edge meaning clock is rising, and that's the or CALC. And here you see RN and timing type as clear, and that makes it asynchronous arc, and it will be half arc. There won't be any rise here. You have only cell fall values. So that's that. And SN, same thing. It's just half arc, and again preset. Timing type is preset. So that's another. And same thing is repeated in output pin QN. CK to Q, and you have RN to Q timing type preset and SN to Q timing type preset. And then you would see some of the leakage powers. So that's our section on timing. I think we are done with timing. I'm going to take a couple of minutes here and come back and start power.